you. Brilliant. So we now have our last speaker before we come back to the panel discussion. So I'm very glad to introduce our final speaker for this mini breakout session, Shan Liu. So thank you very much for joining us, Shan. And hopefully you can share your screen. I will spotlight you. Hello. Are you able to share your screen?
Hello, hi,
Excellent.
Joseph. Can you
Yes, we can see
see
your
my
screen.
screen? Yeah,
Yeah,
yeah.
perfect. It's just on.
Okay, great.
Yeah. Excellent. Thank you very much, and I'll hand over to you.
Okay, thank you for your introduction, and it's my honor to present our research on embodying intelligence, and I would like to share our insights into this topic, and I will share our recent developments on robot embodiment through VISUO-TACTILE intelligence, and I'm leading a robotics lab at King's College London. Our research has a focus on visual tactile intelligence, and I believe this is a key enabler for robot embodiment. So I will introduce some motivation, and I will see how we can embody the robots with the visual tactile intelligence. So first, we can start with some human examples. So in our daily life, we are using both vision and also tactile sensing in our daily tasks. For example, for laundry sorting task, we are using our eyes to guide our hand motions, and the tactile sensing at hand will guide the local motions of these fingers. So through vision and tactile sensing, our cognitive system can guide our bodies to perform these tasks. Similarly, we also have this sewing task on the right. So we are also using vision and tactile sensing together to do these tasks. And for robots, the very first question we need to ask is what hardware available for us to enable the robot to perform these tasks. If we look at our human tactile sensing, so vision is quite common for the research, but tactile sensing is much less explored. So I will focus on the tactile sensing part. For humans, we have a very high density of textiles in our fingers. So we have around 241 Merkle receptors in our fingertip. And there are much less textiles in other body parts, for example, the back or the arms. So there are a lot of development in recent years to mimic these human fingers with tactile sensing. So we have seen different sensing principles from capacitive to piezoelectric, piezoresistive to many others. And recent years, we have seen a trend to develop high-resolution tactile sensing using cameras. Compared to traditional sensing approaches, like we use a sensing element to get the contact for a single cell. So for camera-based tactile sensing, we use a camera to capture the deformation of silicon, so like a human skin. So in this case, we have a very high resolution from the camera itself. In our lab, we have pioneered in these trends, and we have proposed the very first all-around high-resolution finger tactile sensor. We call it gel tape. So we have a camera as the base, and we have a cylinder and semi-sphere shaped the skin. So like shown here. So the camera can capture the deformation on the skin. So the LED lights through the skin can be reflected in the space, so that the camera can capture the deformation of the skin. So this is the picture of the real sensor. So as you can see, it has a similar shape as our human finger. On the right, we have a demonstration of our sensor's capability. So as we have a camera to sense the contact, so we can get the very detailed texture of the objects. Here we have a strawberry model, and we can capture very detailed texture from the sensor. So from there, we can get very detailed information these objects, and we can get the robot to perform these tasks. For example, how to grasp one strawberry. And apart from the hardware, we have also been working on the simulation of the optical tactile sensors. We were the very first one to develop the simulation model for optical tactile sensors, and this is very challenging. So there are a few elements that we have to consider. First is the silicon. It's nonlinear, it's soft, it's very challenging to simulate. And also we have the light distribution in the sensor. So we have proposed the very first simulation model without simulating the silicon. Here we use a depth camera instead of RGB camera in the real sensor. So we have the depth camera to get our to get us the depth map of the context, and then we can illuminate this depth map with colors, and then we can get a very similar tactile RGB tactile images to the real ones. So here we are not simulating any of these silicon deformation, but we are we have some approximations of the context so that we can get a very similar smooth context as in the real world. And we moved from there, and we have introduced a few new approaches. In the previous works, we have seen that in the real world is imperfect. So we have to consider the artifacts in the real world. So we have introduced some manual artifacts to augment the perception in simulation. And also we have introduced the generative models to bridge the gap between the reality and also the simulation so that we can get a better distribution of these artifacts in simulation tactile images. And recently we have developed a simulation framework to get the soft membrane deformation simulated as well, while using these computer graphics methods to simulate the deformation of the silicon, so that we can get a full spectrum of the optical tactile sensor simulation. And also we have simulated the optical tactile sensors of arbitrary morphologies. For example, the gel tip sensor we have seen before. So here on the left, we have the real world setup, and we get the real tactile image. And on the right, we have the simulation setup. We simulate this tactile sensor, and we can get the simulated tactile image. And a key contribution we have got is to simulate how the light travels in the space. So it's more like how the light travels on the Earth. So we can simulate the light passes in the tactile sensors. And we can get realistic tactile images, and then we can get the similar textures and also force fields as in the real tactile sensors. So with the hardware, we have the tactile sensors and we have the simulation models from these simulators. So then the question would be, how can we use the sensors and also simulations for improving the robot capabilities? So the next question is how to learn from this VISUO-TACTILE data. We have, as humans, we have vision and also we have tactile sensing, and we are using both of them in performing these challenging tasks. For example, how to assess hair, and also how to manipulate a flexible cable. So this is what we do in daily lives. In our research, the very first task we have tried is to perceive the textures, to recognize these fabric textures using vision and using tactile sensing. So we have developed this VTAC framework to extract features from both vision and tactile sensing. We can unify them in a latent space, and then we can improve the perception performance of robots. And also we have developed some cross-model research so that we can generate vision data from tactile data and vice versa. So this can improve the robot perception capabilities in a multimodal world. And we have applied what we have done in manipulating these flexible materials. So here we take a flexible cable as one example, and we strengthen it from one end to the other end. We have vision from a top view camera, And we have the kinematic inputs from the robot gripper. And also we have the tactile inputs from the gripper. And then we can feed this state into one reinforcement learning agent so that it can learn its actions from these states. And we have developed these benchmarks, and we have found in this task, vision plays the most important role so that it can get the global view of the flexible objects. But at the same time, tactile sensing can provide very detailed local information, like the pose of the cable, so that it can further improve the dexterity of the robot hands. So that's one example. Another example is transparent object manipulation. As you may notice in our daily life, we have a lot of transparent objects. However, it's a very challenging task for robots to perceive transparent objects and also grasp them. The main reason is that it can, so for the RGB images, it will pose diverse appearance from their background. And also for depth maps, so their body here, as you can see, they have very sparse values. And this will cause some problems for the robot to pick up these objects. So we have developed one vision-guided tactile poking approach for transparent object grasping. So first, vision can give us a rough idea of the location and pose of the transparent objects. And then we can predict a poking point for the robot to contact. And then the tactile sensor on the robot can get you a tactile image, and we can get accurate location and also pose of the objects. And then the robot can pick these objects up. So through combining vision and tactile sensing, the robot can better grasp these transparent objects, and this can facilitate deploying robots in our daily life. So to wrap up my talk, so our goal has been to enhance robot dexterity through visual tactile intelligence. And we have developed optical tactile sensors for perception and manipulation tasks. And we have done sim-to-real learning for object manipulation with tactile sensing. And also we have developed computational models to learn from visual tactile data. And so in future, we will continue to address this challenge. So how to enable, how to empower robots with embodiment with visual tactile intelligence. Okay, so that's all from me. Thank you.
Thank you very much, Xiao. So now